All right. Hello, everyone. Welcome to the Guaranteed Safe AI seminars. I am Orpheus, founder of Horizon Events, a nonprofit agency focused on events for AI safety research and development. The purpose of the monthly series is to facilitate progress in the Guaranteed Safe AI research direction. The session is about 1 hour sharp, usually half presentation, half Q&A and discussion. Note that this month, following the 1 hour event, we will have a 25 minutes social mixer where we can meet each other and discuss in a few breakout rooms. So if that's interesting to you, stick around in the Zoom room after the seminar. Today, our speakers are Charbel-Raphaël Ségerie and Épiphanie Gédéon, with a topic titled Constructability, Designing Plain-Coded AI System. Thank you. The floor is yours.
Nice. Thanks a lot, Orpheus, for the invitation. I'm Charbel-Raphaël Ségerie, and let's present Constructability, a new method for safer by design AI development. So the TLDR is we think using plainly coded AI may be feasible in the near future and may be safe. So we will present this new method, this new agenda, and yeah, we will also present a prototype and research ideas. So how to solve the lack of interpretability problem? Current AIs are developed with deep learning. The AI tries something, gets it wrong, and then backpropagation, and the weights are adjusted. But this leads to a severe lack of interpretability. AIs are essentially black boxes, and we are not very optimistic about post hoc interpretability analysis. We suggest a different method, constructability. Let's try to create plainly coded AIs directly, white boxes, if possible. You think this is crazy? Maybe, maybe not. In the beginning, this agenda was named AI safety via pull request. By pull request, we mean that instead of modifying the neural network with successive backpropagation, we construct and design plainly coded AI or hybrid systems and explicitly modify its code using LLMs. The idea is to use all the software engineering tools and best practices like code reviews, code quality best practices, documentation, functions, unit tests, version control, continuous deployment, and security audits. But we abandoned this terminology, the AI safety via pull request terminology, which is less general than plain code constructability. Here is one possible long-term vision for the plan. So this is one possible long-term vision that we could use with a boxed super coder trained with deep learning that would code a plain code AI, and then we would deploy this plain code AI in the wild, but after an audit. And obviously, this plan is not implementable right now, but this plan might be implementable in the future when language models get smarter and faster. What's the problem we want to solve? If the world released a powerful autonomous agent in the wild, white box or black box or any color really, humans might simply get replaced by AIs. What can we do in this context? Don't create an autonomous AGI is reasonable. Keep your AGI controlled in a lab and align it. Create a minimal AGI controlled in a lab and use it to produce safe artifacts. And we will focus, like this last plan is one important long-term vision for our plan. what are the different benefits of our approach? This constructability would allow AI systems to be, by design, much more transparent. Transparent because the code, we would be able to spot problems much more easily. The code would be editable. We can see the problem. We can also edit the code, and it would be version controllable. All modifications would be made with successive pull requests, for example, and we would be able to trace with Git tooling, for example, with Git blame, why a specific modification was introduced and why. And our hope is to arrive at a method to train models that outperforms opaque machine learning in some important metric. For example, we think that constructability maybe could enable to create faster and more data-efficient models while still being safer than deep learning. Okay, in practice, we would probably use hybrid systems in a first step. So if plain code is too hard, we could use a mixture between deep learning for low-level features, which are not too dangerous, and for the medium and high-level functionalities, we could use plainly coded functions. There is a continuum of transparency. End-to-end deep learning systems are mostly unsafe and there is no guarantee. Plain code models would be nice, but are currently mostly too difficult, and maybe hybrid systems could be a sweet spot of feasibility and transparency. And to give an example of such hybrid systems, here is an example for a vehicle. They used deep learning-based object detection for low-level features, and high-level features are much more algorithmic. So now your reaction should be, okay, but that's very interesting, but surely this is not very feasible. And we will analyze this in the next section, the feasibility analysis. Then we'll analyze the safety properties, and AP is going to present the prototype and some closing words. Okay, feasibility. We'll begin with the track record of automated systems to write plain code AIs, and then we continue with the track record of humans to write plain code AIs. Yeah. A very important example that we think we could generalize is Stockfish. Stockfish is a superhuman chess engine that did not use deep learning before 2020. It was quite understandable back then. And Stockfish had an automatic system for testing pull requests. Something very important is, while Stockfish was during the plain code area of Stockfish, Stockfish improved by more than 700 ELOs while keeping its code constant, the number of lines of code constant, almost. And yeah, so that's one important idea, important track record. And we think that it may be possible to generalize this idea. But maybe you might think that, chess is easy, is very easy to specify, and that's not the case of what we want to do. And yeah, you are right. For example, in the original reinforcement learning from human feedback paper, it seemed like getting the essence of backflip in a single handcrafted functions would be always inferior to deep learning and to using reinforcement learning from human feedback. So let's open the link. You can see on the left, there is this nice backflip. And on the right, there is the backflip, which was obtained after crafting the reward function manually. And the backflip is not as beautiful. But this was a few years ago, and today we have GPT-4. And GPT-4 with Eureka is able to do amazing things like this, to craft a reward function that enables the robot to flip this pen, which is very, very impressive. So let's come back to the presentation. Yeah, so GPT-4 was able to write a reward function for something which is like this, with a plain code reward model. And yeah, no need to understand everything in this code, but you can see this pull request, which is quite understandable. And something very amazing about Eureka is that it's also possible to obtain a superhuman reward model. Eureka is able to exceed human level to write plain code reward functions. Amazing. So yeah, Eureka is very similar to what we want to do. Only instead of writing only the reward function, we would write explicitly all the policy. Did you know that GPT-4 is able to play in Minecraft? When GPT-4 was released, we didn't know it was able to do so. But in fact, with the right scaffolding, GPT-4 is able to play in Minecraft, and the system is called Voyager. Voyager is an agent that interacts with the world, and that codes functions to broaden its abilities. Voyager can create this skill library, and each skill is a function that was created by GPT-4. And yeah, we can read the lines of codes, we can check each function, and we have a controlled skill library. And we have much more control than with reinforcement learning. And yeah, Voyager is also very similar to what we want to do with constructability. Let's continue with the track record of humans. Okay, we presented Stockfish. We presented Stockfish, but here are some other examples. Watson is an expert system capable of answering questions in natural language and won Jeopardy against humans champions in 2011. You can see an example of a question. Another example of plain code system is the automatic pilot of the moon landing. Face detectors can also be handcrafted. Yeah, so this is an example of such system back in the days. And yeah, much more systems are impressive and plain code. Okay, let's continue with the feasibility crux. How possible it is to create a system that beats AlphaZero or GPT-2 with plain code. We think that there is this important crux that we name the non-connectionism scalability. How possible it is to create something that beats GPT-2 or AlphaZero in a plain code or hybrid way. How necessary is it for models to be connectionist to do this? So yeah, that's the name of the crux, and let's try to look at the numbers. So here is an extract of what will GPT 2030 look like from Jacob Steinhardt, and from his super forecaster, and he says that yeah, GPT 2030 will likely be superhuman at coding, hacking, math, And the organization that trained GPT-2030 is going to be able to perform 2 million years of work when adjusted to human working speed. So it's a forecast, but it's an interesting forecast. Okay, so let's say that we have a budget of 2 million years of work to achieve AGI in a plain code way. Okay, how many lines of code?
I'm like kind of bent into this meeting.
Yeah, how many lines of code do we need to code humans? Say someone learns one new concept each minute for 20 years, that's only 10 million concepts. And if we need 10 lines of code per concept, that's 100 million lines of code. And macOS is also 100 million lines of code. So we already did it in some sense in the past. And how long would it take to code this amount of code? GPT-2030 produces 2 million years of highly qualified human work each 3 months. And macOS was approximately 100K years per son of work. So yeah, when we try to run those numbers, it's a good sign that we can iteratively improve pull request after pull request the code of our plain code AGI. Okay, what about superhuman concepts? You might say that, yeah, but like in order to do this, we might need to take superhuman concepts and write them into code. And you might be right, we might need to do this kind of thing. But there is a paper from DeepMind that succeeded in extracting superhuman concepts from AlphaZero and teaching those concepts to chess grandmaster. So it might be possible to some extent to extract knowledge from superhuman AIs. And another objection could be the bitter lesson. So we think constructability is not in direct contradiction with the bitter lesson, because the bitter lesson is mostly saying compute plus search is necessary. But it's not saying that deep learning is necessary. And we would also leverage compute and search at scale to do constructability. So yeah. So that was it for the feasibility. And I will let Epiphanie continue with the safety properties.
Yeah, thank you. So of course, whether or not it is feasible, there is a question of whether a model is safe and whether our approach in system in general is safe. So as mentioned earlier, we would have automated safety mechanisms. For plain coded modules, we would have automated code review with LLMs, and of course, human overseeing this process before anything gets merged into main branch and tested further or deployed. But for shallow networks, we would have something more interesting, which is, basically, we would have something we call an oracle simulation, which is a black box word model, think Sora or something like that. That we could put our agent in and observe how the agent behave with the world, and have automated LLM system look at the behavior of our agent, but also automated LLM system that looks at the behavior of the world itself and ensure it is consistent, and fine-tune it for it to be more coherent and for it to exhibit more of the kind of behavior that throw our agent off. And in addition, we would do this decomposition again and again. So we would start with shallow networks or any kind of deep learning network and decompose them further and further, both to adjust to the type of data that it did not have previously. But also, there is one very interesting aspect of it, is that if we can decompose a system again and again in a way where we keep the same overall performance and then we can have a sort of metric for alignment, because if we decompose our model in a way that we can understand, in a way that makes sense to us as an ontology, and it still works, then this means it is behaving in a way that we would want it to behave, basically. So what is the long-term vision of constructability? So one key point of difference that we have with respect to other safe by design agendas is that we do not focus on building an AGI or general purpose agent. What we would focus on is scaling up automation. And we would want something that, given any task, it could produce an agent that is able to do it. So we wouldn't want to have an agent that can learn to do the dishes. We would want a system where we can ask it, hey, please write a robot who can do the dishes, and then it would produce that. And so that is one difference. So as we mentioned earlier, we could have this agent be centralized into a single lab. But one aspect that we're very excited about is the notion of soft pivotal act. As we've mentioned, there are many advantages of constructability over other kind of approaches like deep learning. So one key aspect besides transparency and editability is the inference speed and how small the models can be, and how parallelizable it can be, and how we could train it way faster in a way that we can fine-tune and understand where it went wrong each time. And the reason this is exciting is that there is a way for it to become a more popular approach to machine learning if we push in this direction and have industry adopt this system. And then we could replace progressively current systems that are using machine learning with something more understandable and more constructible. And then we believe this would be way safer than our current status quo situation. Of course, we could do the decomposition of GPT into mGPT-n-1 submodule and continue until we have something plain code-like that we can then use its insight to build onto robots or like systems that are currently, and do this kind of substitution mentioned earlier. And that would be exciting. All of that, though, is very dependent on one key aspect, which we are very uncertain about, which is autonomous replication and adaptation. Because especially the last point would be very dangerous for it, in the sense that if a model can be able to replicate itself in a way that it can modify to avoid detection and to adapt to any kind of way we want to catch it, then this would be very dangerous. And constructability especially would boost the very first steps of ARA. And so we would want to find what kind of research ideas would not boost it, and whether ARA is dangerous and how it would look like in such a situation, because only the first steps would really matter. Once it gets to a certain point, we wouldn't be able to do anything about it. So where do we stand in relationship to other safe by design agendas? So according to the guaranteed safe AI framework scale, with what we have said so far, we would be W1. We have a world model that is a black box. We would be S2 or maybe S3, in the sense that we have LLM automatic reviews, and those uses predicates that we would define. And we have V5 for shallow network, and for plain code module, we could be up to V10 because you can do anything with plain code. But all of that is only with what we've outlined so far. The advantage of our PR loop, where we modify again and again, is that we can tack on any test that we can think of, and we can tinker it as we see fit, basically, if we feel there are ways for it to be safer. Another difference is that we focus on specifying the policy directly. We don't actually focus that much on having a world model and having this world model be well specified. We think it is way easier and faster to have directly the policy and to see the heuristics and how it behaves. And either prove that directly or use it, or use unit tests to test how it would work, basically. And so that is one reason that this framework does not apply as well, in the sense that it focuses way more on world modeling. So we had some assumptions that we wanted to test and explore in order to understand how feasible constructability would be right now. One main aspect is compositionality. It is this notion of we have a module and we want to substitute it with other submodules. How much drop in performance do we have? Is it stable? That kind of thing. And then we wanted to know how overseeable it would be and how we could understand what was going on. And if we had a way to have more interpretability by design in training it on very specific subtasks. So that is why we did unexplainable, which is a sort of proof of concept for what would an ImageNet recognizer look like using this PR approach of deconstructing modules further and further. So as a proof of concept, we focused on the very simplest classes of ImageNet, which is daisy flowers. And we wanted to have 70% accuracy and to have each submodules be very small in size, less than 1,000 parameters, and only 3 layers deep. And so we used a very simple ontology. Flower head is a petal plus a center disk. Flower head plus a leaf plus a stem is a flower. And so each of those nodes are networks that are trained against each other. That is, a petal network tries to recognize what is a petal versus a center disk versus a leaf versus a stem. Importantly, all of those networks do not have access to any kind of non-flower dataset. Only the topmost layer has access to it when it tries to classify them. And so what we have done is compose a petal plus a center disk into a recognizer, which I will explain later. So how did we train a neural network? What we did is we have many segments from our dataset. Here you can see we have a segment of a disk and a segment of a flower head. And you can see that even though the segments are the same, like one is included in the other, the neural network has to understand that this one is a disk and that is not a disk and that is not a disk either. So we pass that through 3 layers of convolution. Then it outputs a very small image. Those are not factual image, but it outputs 4 numbers that get then into an inference head that we will cut off later. And the inference head is either a max pool or a short linear network. We have tried both. So it tries to output the probability that this is a disk or that this is not a disk, basically. And then since it was trained on very small segments, we can use them directly onto bigger images without any kind of refinement. And that is what we have done. So here you can see those are actual images that the petal network has actually a good understanding of where the petal are. And the same way for this network, even though they don't have any kind of understanding of compositionality, or they haven't been trained to recognize where petals were. They have just been trained to recognize what is a petal and what is not a petal. And that is something that we are very excited about because it means that constructable approaches may work well. And then we pass it through another layer of convolution that is trained the same way I explained earlier to have an image. And this convolution cannot see the original image. It can only see the outputs of the other layers. And so it can only know, oh, there are petals here and there is a disk here. So that means that there is a flower. So what are our results? We have found that compositionality works fairly well in the sense that we have attained 75% accuracy, whereas a direct layer from end to end, that is 1,000 parameters, is 85% accuracy. And one aspect that we did not expect is that we have been able to swap submodules for one another, even though they were trained with different architecture, in a way that we had minimal drop in performance. And yeah, we have found that instability does seem to add up in the sense of the model being more and more erratic. This is less the case with max pool head. However, Maxwell heads are very erratic to begin with, so we would need to find a way for it to compose well in a way that would be more stable. We have also found that actually the subnetworks have had poor subinterpretability. However, we believe that this is because the dataset have not been secluded enough. Like a petal is both a pink petal or a white petal, and a disk is either a yellow disk or any kind of disk. And we think that if we could seclude them more and more into very similar images, then this would work way better for us to have something that we could then interpret and reverse engineer. We have many research ideas to expand on. I won't get into all of them, but basically we could want to scale up our prototype to see how far can we go with classes recognition and see it in action with a GitHub, and use this idea I've just mentioned of decomposing a system in a way that we understand how it decomposes. So replace the compositional layer that are neural networks of 20 parameters, of 30 parameters now, and use plain code to say, oh, okay, there are disks here, there are petals here, so that means this is a flower or not, basically. And yeah, like expand on the notion of Voyager in this PR loop and expand on the PR loop. So in conclusion, we think that constructability is very interesting on the technical side and that it might have an actual impact. Especially it can be quickly prototyped and iterated on in worlds where it matters. And especially if we have a way to centralize in labs and we can boot it and we can see how it would go. However, we think that there are things that are more important right now, and more importantly, in a world where they are relevant, they are very, very urgent. One aspect of this is that we still don't have a way to regulate open weight models. We don't have any way to prevent a company to just torrent and publicize like model weights, basically. And this leads to warning shot theory, which I will let Charbel explain.
Yeah, there is one important hypothesis for constructability to work, which is safety culture. We think that safety culture is really important to get the next decade right, and we are probably not on track. Some people hope that some warning shots would help humanity get its act together and change its trajectory to avoid extinction from AI. However, we don't think that's necessarily true. There may be a threshold beyond which the development and deployment of advanced AI becomes essentially irreversible and inevitably leads to existential catastrophe. Humans might be still happy while not even realizing that they are already doomed. And there is a difference between the point of no return and extinction. And we may cross the point of no return without realizing it. And yeah, any useful warning shot should happen before this point of no return. And we will need a very, very convincing warning shot to change civilization's trajectory. So let's define a convincing warning shot as more than 50% of policymakers want to stop AI development. What could be examples of convincing warning shots? For example, a researcher I've been talking to, when asked what they would need to update, he answered, an AI takes over a data center. And I think this would be probably too late. So the priority for the Center pour la Sécurité de l'IA, the CeSIA, will remain safety culture. That's our priority as long as people in the world continue aiming blindlessly towards the event horizon. And we think that, yeah, autonomous replication and adaptation might be one of the point of no return. We don't think autonomous replication and adaptation is going to be an existential risk, but it might be very possible that 6 months later on, after we get an AI which is able to self-replicate and adapt, this AI is able to create a successor model. For example, GPT-6 creates GPT-7. And we think that this might be probably too late. So we might need to stop at autonomous replication and adaptation, but are we on track for this? Maybe, maybe not.
So in conclusion, that is why at CeSIA we are focusing on building a warning shot response team. That is a team that can answer to events like CrowdStrike, Bing, and XZ, and have them be publicized and have the public understand what is actually going on. Because even though they have had major impacts, the impact in public understanding of how fragile our current architecture and system are has been very minimal. And so we want to change that, and that is what we're building on. And also we want to work on impacting the mimetic landscape, both through demonstrations and working on applications that people can share, and have everyone understand more what is going on, because that is our main theory of change for how people will react and how we can actually try to put an end to it. Thank you very much for your time.
All right, thank you so much for the presentation. Round of applause. So we have about 22 minutes for Q&A and discussion. There are a few questions in the chat, and we can go in order, chronological order. So the first one is from David James, and so if you want to show up and speak your question, that's best. And then after we go through the questions, we can have a general discussion.
Thank you. Yes, I think one of the approaches to make AI safe is that perhaps we have segmented the capabilities of different models, perhaps the knowledge of different models. And when I asked the question, it was pretty early on in your presentation. I don't know if that factored into some of your thinking. I may have missed if it did, but kind of an open-ended question to see what you think about segmentation, if that's even the right term for it. Also, compartmentalization might be that might be a better name for it.
So the word I have been using is decomposition, like taking one module and decomposing it into several submodules that then we would use its output to compose it to have it perform something. Is that what you mean, or is that something different?
There could possibly be overlap, but I'm thinking about the case where you have two AI agents, and perhaps one is trained with a very detailed knowledge of, say, formal code analysis, and another is trained without that, but with a very detailed knowledge of, say, cybersecurity exploits. And you make sure that no one model has enough to be dangerous. That's the idea.
Oh, okay.
Yeah, we didn't thought about this, to be honest, but that's something we could incorporate in the plan, probably. Yeah.
So yeah, I would add that, like, our hope is that by having very simple and shallow networks, they can't have a very complicated understanding of the world. And so we can both look at the output of the network to understand what it does and to have reviews of it. So basically, it is a bit ingrained by design, this notion of segmentation, in that we would have like one module that does cybersecurity and another that does something. But the point that is more relevant to your question is that the agent that could decide to use both of those notions is written in such a plain coded way that we would be able to understand, it is using the output of this agent that has access to biosecurity. We want to be very cautious about what it does and track the flow of information from it, basically.
Thank you.
Cool. Next question, actually, next two questions are from Raf Kaufman.
Yeah, hi guys. Good to see you guys, your faces. I've been following this work since the original last prompt post, so it's pretty cool to see the full presentation. The first question is more tactical. I didn't get the in the stockfish slide you mentioned something about some number of automatic PR loops, and I didn't quite get in what sense that was automatic, and if it's just in the sense of there's some like automated checking, non very intelligent automated checking, what makes that different or special?
Yeah. Oh, sorry, did you?
No, but I mean that's comparatively less relevant than the following question, so I'll just ask that one. So my question is if you think about a very large plainly coded system, like with multiple billions of lines or however many ends up being necessary to do the kinds of things that we want to do with advanced AI, is that really human interpretable in the sense that obviously it won't all fit in somebody's head, and even if you like factor in compositionality and abstraction and all of that, it's still going to be too complicated to fit in one person's head. So you are relying on some sense of a collective of humans to collectively understand what's going on. But then does that really mean, is that really interpretable in the ways that are relevant for this?
So like we could ask the same question for the Google code base.
Yeah, 100%. Yeah, this is coming from working 6 years at Google and having to deal with developers that spend my work was trying to help developers interpret the Google code base, or at least some chunk of it.
Okay. Yeah. I don't think it's, that's a very good question. We think that, for the code to work, for this approach to work, we need to follow like best practices. For example, documentation is going to be essential. Having successive, like constructability is not necessarily AI safety via pull request, but we think that pull request would be very neat because we would have like an automated kind of documentation to know from like what was the process to incorporate this feature. And obviously we need scalable oversight to work to scale this approach, because a single human won't be able to review everything. So we want to delegate to language model as much as possible. And scalable oversight is probably necessary for this agenda.
Yeah, just to emphasize that Google is famous for being quote unquote pull request Nazis. Since the monolithic code base, everything can break everything. So depending on the size of the PR, you have to have multiple code reviews, approvals, full-fledged design doc, and so on. And it can be argued that that's not helping global interpretability. It might help local interpretability, but it just makes the navigating the whole mess even more difficult.
Yeah. For me, I would say that the main question is in connectionism. Basically, like if we can have many small repos that we can understand what each of them do, like you can have the work cycle repo, and this one is maybe like 5,000 line of code or more, I don't know. Then you don't need to have an understanding of the whole code base to review it. And then it is okay because you can segment it. And so the main question is, would we need to have all of the concepts together for it to really work? Because in that case, we would be in the situation you described where we would need to understand all of the code base at once to really have any kind of progress. But if we can decompose it into very specific tasks, then I think that we are okay, because you don't need to understand all of the other submodules. You can just say, oh, this is a module that make us work, and then we would be more okay, basically.
There can be emergent behavior in these complex models, but we can.
Yeah, exactly. That is kind of my crux. Like, how emergent do we need to be?
All right. So next question by Gunnar.
Yeah, I like your engineering approach of working with pull requests and having some kind of compositional approach. I wanted to ask what classes of combinations or what kind of structures of these neural networks and plain coded modules you envision. Like these boxes that you've shown here are relatively straightforward linear chains, basically. What I've seen and what, for example, what the company I'm currently at has been doing is that there's an LLM and then there's some plain coded part and then another LLM is called, and then the interface between these boxes is then just tokens, right? Text. So, and I wonder what kind of boxes, what kind of, is it just always a DAG? Like, is it just with neural networks at the bottom? So what kind of, what constraints do you imagine on these potential very many ways to put plain code and neural networks together? What kind of classes do you have in mind, or where you see the highest benefit?
Yeah. So why do we, in the diagram, why do we use this hierarchical composition? It's because we had ImageNet in mind and vision recognizer, vision classifiers in mind, CNNs, and CNNs, like in some ways, like between different layers, we can abstract a bit the idea of a graph composing from different feature maps to other feature maps for the next layers. And so that's why for unexplainable, we used this tree structure, this hierarchical tree structure and obviously this idea of a tree is fairly natural to go from CNN to plain code CNN. And what we want to do, we think obviously it's going to be much more complex data structures for language models. For this, we have less ideas on what's the best data structure.
Yeah.
Okay, so next question is Raf, but for now, let's go to Daniel.
Cool. Yeah, I was curious about for the prototype. It seems like you're connecting together a bunch of different neural networks and passing like the output straight into the inputs. And I was trying to just figure out kind of for myself what separates this from thinking about it as a single neural network that has a weird shape or architecture or whatever versus thinking of it as something like fundamentally different. And I thought maybe it was the fact that you don't backpropagate across the whole thing, but I'm curious if you could try explain that again.
So there are two aspects. The first one you've mentioned is that, sorry, I'm trying to find back the slide of, this one. So one aspect is that we don't have backpropagation. Like we train each neural network separately. So the petal neural network has no idea of what the disk neural network does. And another aspect, like why is it important, is that we can inspect, like we have basically checkpoints. Like we can inspect, oh, is the petal neural network working correctly? Is the disk neural network working correctly? And swap them or fix them kind of independently of each other. So the main reason we don't see it as a single neural network is that it has very like delimited paths that we can tweak basically. And so the full prototype would be full of those. of very small parts that work together, and we can understand what each one does and where we would want to fix one if something were to go amiss, which is not the case with like a big neural network. If it doesn't work, you just have to retain everything or fine-tune it or something like that.
Makes sense. Thank you.
Cool. So I think we're out of questions in the chat, but I think we still have a few minutes left. And so if anyone wants to ask a question on their mind or just a discussion topic, feel free to raise your hand or just pop in.
Yeah, I had mentioned this in the chat. I think it's a really big proposal you've got. It's almost like a meta proposal or a schema for thousands of proposals. And I think there's so many parts that it's actually kind of challenging to solve within the realm of just AI safety. I mean, for example, the parts about how to have a good security culture. There's a whole literature about that from, nuclear monitoring, for example, and the cases of how to run good pull requests. That's almost a sociological study of how different cultures do this and make sure that people feel comfortable speaking up. So I feel like it's a huge area. I think it's interesting. Just curious if you're mindful of just how big this is.
Yeah, I would say that definitely. Just a small point is that safety culture, like in my understanding, is not part of constructability. Like it is kind of its own thing that we would want to focus on. But yeah, definitely, like that is kind of. So on the one side, what you're saying is completely correct. One aspect that I would want to highlight is that it is very prototypable. Like we don't need to get everything right. We can just start with a GitHub that we have some kind of automated PR loop, like for a very simple task, and see how it behaves. And then we go on something slightly more complex, and we would iterate and see any parts that are missing as we go along. And to me, that is one aspect that is very promising about these agendas as compared to others, is that we can like directly start on it and see how it works without having to get everything right at first.
Yeah. Just to mention, it was maybe 2 presentations inside one, because the first part was from the post Constructability, and at the end, when I presented the part with warning shot and warning shot theory, it's from another post, which is named "What Convincing Warning Shot Could Help Prevent Extinction from AI," which is also on my list wrong. And yeah, in this other post, which is much more sociological, as you've seen, I detail a few important questions about warning shot, and obviously those questions are completely different from the constructability agenda. It's like 2 modular agendas.
Hey. Interesting work, very cool. So in your original Less Wrong post, you mentioned, this comparison with connectionism. And, do you feel like if connectionism and emergence from larger networks happens to be a kind of a fixture, do you feel like that is a kind of death sentence to this framework, or do you see a way forward that's like harmonious with that fact?
Yeah. So there are 2 questions here. There is the question of the probability of is like what we think about connectionism, like is this going to be necessary, and the question about if it's really necessary, is like our agenda, is it going to decay gracefully? And for the necessity of connectionism, I have a sense that it's not necessary, because we showed many examples, for example, stockfish, and maybe connectionism you could be much more superhuman with connectionism, but if you just want to reach AGI and not necessarily superhuman, maybe connectionism is not completely required. And the brain is not completely connectionist when you think about it. Like, there is a lot of connections, but not like one neuron is not connected to all the different neurons. There is some modularity, some limited sense. And so
even
that's,
sorry.
Yeah, sorry.
Well, I was just thinking that, even if connectionism is a strong property, I think there's still a lot of room for this framework to play, especially with the pull request framework and constructionism. I think it can still be an important framework.
Yeah, I would say that if constructionism is very necessary, then we would pivot into understanding where the lines are, basically, like what can we do with this? As Charbel mentioned, like stockfish is actually a very good example. Like, yes, you can get with deep learning 3000 ELO in chess, but with just plain code, you've already beaten every kind of human there is. And so, like, how much do you really need to go, basically, is one question. But yeah, like I do think that understanding how much compositionality works and how much connectionism is required would be one of the main pivotal questions that's,
Thanks.
we need to solve.
Yeah.
All right. I think we've reached the end. Thank you so much for the presentation.
Thank you.